we can start. And for the next talk, we will hear about towards structured algebraic programming, and the talk is given by Daniele.
Thank you so much. Yeah, so this is actually a joint effort with other colleagues from the Computing Systems Lab in Zurich and also from the High Silicon department. The first thing I would like to do here, so we are talking about structured algebraic programming, but is to introduce what I mean really by algebraic programming in the first place. And I have to say thanks to Guide for having introduced in part, at least at the high level, an interface that is very helpful to describe the logic of algebraic programming. So here I'm showing an example, an implementation of one of the existing C++ interfaces for GraphBLAS. And so, so he has introduced a little bit the concept of GraphBLAS, but the idea that I really want to capture here in terms of algebraic programming is the fact that we have a bunch of primitive building blocks, like the numerical primitives that he has been using in his implementation, like matrix multiplication, matrix vector multiplication, and so on. And these primitives are generalized over algebraic structures. Okay, so for example, in this case here, we are building a semi-ring here, a mean plus semi-ring in this case. We are trying to compute here the k-hop single source shortest path starting from a particular node in a graph, for example. Okay, so the graph would be represented by the matrix of its that kind of represents the different edge connections in the graph. And then you have an initial vector where you maybe set your source value, right? So it, as shown here. And then, you know, we iterate k times by multiplying the vector and the matrix and the incident matrix. And this allows us to basically proceed through jumping through neighbors, right? So this is a simple example there. So the algebraic structure is clearly one example, one component of the algebraic programming concept. And then the other is the fact that we have a container, and these containers are opaque. And we can use these to kind of abstract the logic of the storage, whatever is behind, and is kind of decided by the framework in a way, and abstracted from the user, right? So the user does not need to know what's happening. It's just providing a mathematical specification. So the opaque containers here, I'm just showing the example of the vector and the primitives, right? So these are the three kind of key ingredients that I have in mind when I refer to algebraic programming. And you know, one thing is that in graph analytics, for example, is very useful because, as Guide also has shown, you change the concept of semi-ring. For example, here I'm going from the mean plus semi-ring to the Boolean semi-ring. And all of a sudden, even if the program doesn't vary much, it's just, I'm just changing the concept of semi-ring and the concept of set associated with the container. And we are going from an implementation of the k-hop SSSP to a k-hop neighbors, for example. So it's just basically varying the logic associated with the semi-ring. This has been, in the GraphBLAS context, you know, explored for many algorithms. Okay, so here I'm listing, I'm pointing to the GraphBLAS pointers, which is a web page in the GraphBLAS.org webpage, and they try to collect where a lot of algorithms where this concept was applied and the algorithm were expressed using GraphBLAS basically. But also the very same concept was applied to dense tensor containers. In the case of dense tensor contractions operations. Maybe the table is a little bit small, but basically here what this column would show is the concept of semi-ring applied in the tensor contraction, okay? And in this work, basically the logic of the algebraic programming logic was leveraged by compiler techniques, okay? So you could use it to basically plug different semi-rings within the same compilation strategy for tensor contraction, okay? So in GraphBLAS, a lot of the logic happens at runtime. For dense containers, compilers would be a better place to put the logic, because you can do loop transformations and things like this. And this work was one of the first recent work that actually fell under my radar that applied similar concept, but in a compiler context. And now, so one question that we are trying to answer in this work is, okay, so what if we want to extend this logic to apply to dense containers, but in a way that they can be useful to implement things like scientific applications and so on and so forth. So if you want to go into old but also new emerging algorithms, you need the concept of structure as part of your interface. So what we are, for example, here I'm showing, like, this is a recent work from supercomputing where they were taking, they were trying to implement essentially a Cholesky decomposition, if you want. And the traditional approach would just create a homogeneous decomposition of the matrix with a particular precision for the data set. And in this case, for example, the gray blocks here are dense blocks with like classical column or row major storage layout and a 64-bit precision, floating point precision. And they show how essentially, in order to scale to the Fugaku supercomputer, these kind of algorithms, as part of the application that they were targeting, the best thing they could do, it was actually to go into the classical implementation of Cholesky decomposition and introduce mixed domain, mixed precision, and different kind of layouts for different blocks. So the left part here is the part where they kind of investigated the mixed domain, mixed precision. So here, for example, they realized that the most important information lies around the diagonal, essentially, that's where you want to keep dense, high precision kind of information. But then the moment you go down, you can lose this, right? And also they realized that they could also use a much, much more lightweight storage for those blocks, okay? But of course, this does not fall into the classical storage or the classical implementation of the high performance libraries like LAPACK that you would find out there, right? So they had to implement something specific for this. But besides the implementation details, one thing is that clearly also they also realize is that the APIs itself would require some form of extension, because these things are not really captured by today's APIs when it comes to numerical computation. And so, this is an example of essentially on the line of GraphBLAS, but also considering the idea that we want to capture structures, how we would envision this API extension, okay? So we have defined what we call algebraic programming, which is the framework on top of which we built this extension, shortened up in ALP, because we are in Switzerland. And essentially, ALP dense would be this extension of GraphBLAS with structures. And you see, we still have the concept of semmering that is, for example, useful if we want to go to things like mixed precision. So we would embed this through the change of semmering, in a sense. And this is already somewhat supported by the framework. But then I want to say a little bit more about the concept of structure. So how do we extend these from the API point of view and perhaps integrate this into the type information? The framework where we have built this extension, as I said, is the ALP framework. Here I'm giving like a very simple schematics of the framework. In fact, we have seen Cocos. It's a little bit on that line. So the idea is that you have a high-level API, right? Essentially data-centric, sequential. In a sense, you don't really think of parallelism too much. You think more of the math, in a sense. The more mature interface is currently ALP GraphBLAS, so the one that I've shown you to implement the two simple algorithms. And then we have a bunch of backends. These backends basically represent the computational paradigm, right? So if you want to run on a distributed system, then you would compile using the distributed flag, and this would basically implement the API using a distributed system in mind. But without changes at the source code level, essentially. Okay. So this would be managed by the framework. And the opaqueness of the container also controls the logic of the storage, the allocation of the memory, where things are stored, and so on and so forth. And then you have a set of targets that are essentially in between the API and the framework. And for this extension, we started playing a little bit at the sequential level, so it's all like a preliminary implementation. So we have the sequential reference implementation, a little bit of shared memory, scratching the surface there, that I will show towards the end. The proposed API is ALP-dense, so it's not really GraphBLAS, which is not visible here. It's still available, though, in my slide. It would be on the right, just a little bit more transparent. But it would be like a separate thing. So it's a little bit on the line because it's still algebraic programming, but is not currently a GraphBLAS extension. And we are targeting a Kumpel 920. That's from the high silicon department. It's a server-level CPU. It's essentially an ARM v8 ISA with 2 sockets, 96 cores. And the summary of the API extension is as follows. So what we would like is the user to have in mind the math. So we have the container on the left here, what we call let's say, the math layout. So the user perspective is on the math layout. And what we want is the user to be able to express a structure and the fact that the data within the dense part of that matrix is dense. So dense meaning that there is an actual static mapping, in a sense, between the logical layout and the storage, okay? In principle, one could have an upper triangular matrix which is also sparse, right? So it's still a structural information, but you would use maybe a different storage layout for that. On the other hand, the concept of storage, the physical layout, if you want, it's hidden, in a sense, from the user and managed by the framework, okay? So, and this means that the same logical layout through a different AF, which is an access function, we will define this a little bit later, shortly. It will basically, as a function of the structure, the kind of views that you have on the container, the density and the backends that you choose, might select, for example, different way of mapping a particular element to a particular location in memory, okay? So, for example, on a pack sequential format, we would, for example, just represent the non-zero pattern of the matrix without storing the zeros. Or if you're, for example, in a parallel settings, we may want to use a block cyclic parallel format layout for the matrix. So the opaqueness of the container is exploited to decouple this interface. On the other hand, we have the views. So views are essentially intuitively, a manipulation of the container, but that does not require necessarily new memory allocation. Okay, so we might want, for example, to see the transpose of the matrix, right? And the transpose of the matrix would be, number one, a different kind of structure matrix, so it would be a lower triangular matrix in this case, right? And so we would like some way to represent this in the type, so something that allows us to track this. Also, we have a concept of functor view. So, for example, as in the application that I've shown from the C paper, you may want to take a rank 1 update kind of multiplication. So where basically you have a rank 1 matrix, the red one here, but where every element is essentially instantiatable as the multiplication of 2 elements in the same vector, in this case. Moreover, being the same vector, it would also provide symmetry. Okay? So the rank 1 multiplication between a vector and its transpose is a symmetric matrix. So there is a lot of structures that can be tracked through this, and does not necessarily require to store an entire matrix. We might just store the vector, and for low rank operations, we might just want to be able to access the source vector for that. So here, just a quick high-level picture of what we mean by access function then, okay? So an access function is essentially a component in the interface. So this is typically an internal component, so they're the namespace, that is available for the framework developer, so those who are implementing the backends, for example, okay? And they essentially provide the logical mapping between, the logical coordinates in the matrix, so to say, and the storage position, right? There are two key components in this access function. So one is what we call the storage polynomial, and the other is the row and column maps. Okay, so these are two components that kind of essentially in the logic combine as, you know, you have a polynomial that represents the storage layout. You can think of it in the high level. And the row and column maps allow you to identify some mappings between the logical coordinates. And then you apply this within the polynomial to retrieve your position in memory. So let me zoom in into the storage polynomial real quick. So what we mean by storage polynomial, we really mean like a concept of bivariate quadratic polynomial here. So we chose this particular family of polynomials because we found it's rich enough to essentially support major storage formats that, for example, we would use for implementing LAPACK algorithms, in a sense. So it's essentially composed of static and dynamic factors of the different terms, right? And they are all integer variables and coefficients. So the static coefficients would be essentially, you can think of them as compile time optimizations enabler. So let's say you know that a term is 0, you can use the static coefficient for zeroing out completely at the compiler level the component, the term. Or it could also, and it allows also, like as you can see there, there's like a denominator factor D, right, that can be used for fractional compact storage. So if you want to show, for example, I showed the concept of packed format for triangular matrices, then you can use that to that factor to represent essentially that kind of mapping. And essentially as a piecewise polynomial formulation of this, so you can think of it as the union of these guys, you can also represent maybe structures that are union of bands, essentially. This is like a general, essentially like the kind of general structure that you can represent with this is a union of bands. You can take this as a high-level picture of what you can do with this storage polynomial. And so here I'm just showing how classical, you know, polynomials would represent classical layouts, like so the linear 1D row major, or the linear 2D for a matrix, or the triangular packed. So they would be all a kind of combination of static or dynamic coefficients. Also, we have, we do not want to limit the concept of polynomial to being a scalar function, of access function, sorry, as a scalar function, but rather multidimensional one in general. Here we started experimenting a little bit with like this formulation of the access function, which in this case would be a 5-dimensional one, that is useful, for example, to capture things like 2D block cyclic layouts. And where basically the last dimension that you see there, the location, is effectively the sequential scalar, storage polynomial that I was referring in the first slide, in the previous slide. And so this is one component. The other component is the row and the column maps. Row and column maps are essentially very similar. They are just a subset because they are implementing the concept of affine mapping. Okay, so these are essentially interval functions that you can use to express things like subset of rows or columns. Okay, and they can be expressed as affine maps. Okay. So here I'm just listing some of those that we have tried out. So identity, stride, zero, constant, select. Select is actually a dynamic form of function, but I will focus here more on the static ones. So the strided one, for example, at the internal interface level, could be used to get a view over a matrix S with two ranges. And so we would create like a smaller matrix, a view of a smaller matrix within the larger one. And this can happen by the moment both the storage and the row and column maps are static by essentially composing them. Okay, so one form of optimization is the composition of these concepts. And the storage polynomial might, at this point, incorporate the whole logic of the row and column maps combined with the storage polynomial information and create a unique map that can be used by, without having to compose these things at runtime, essentially. So here, for example, in the strided case, I'm not putting any math, I'm just putting a recipe kind of bullet points. So suppose you have a strided map, a row or column maps and your polynomial, then you would just substitute the row and column variable with the affine mapping for the stride, right? And then you would bring the polynomial into canonical form. All this is implemented in the backends essentially using static polymorphism right now in the reference backend, okay? And of course, the composition can go on and on. So you could have some kind of telescopic views developed based on this concept, right? So you could you view a submatrix of a submatrix in a sense, and you could still, if all these mappings are static, you can still build a single storage polynomial formulation, a single one out of it. Here are some examples of the essentially kind of views that we can support based on this concept right now. So we can, of course, see reference-like views, change the structure of things. We can transpose or take a diagonal of a matrix. All these things are essentially expressible using the concepts that I've shown you in a way. And one last aspect is related to, the structure itself. So how do you, so what else can you, so this is from the storage mapping point of view. Another thing that is enabled by the API extension we have created is that we also create some kind of connection that can be used by the compiler to reason, for example, in terms of type traits currently in the reference implementation about relationship between structures, okay? So on the one hand, we have the band intervals information, so this non-zero static geometry concept. So here, for example, I'm creating a couple of, a union of bands, as I was mentioning, where we have intervals that express the bands that compose the non-zero pattern, right? And this can be used to express the matrix structure. And this is essentially capturing plugging in numbers into these polynomials that I was discussing, that I was introducing. Logical relationship with other structures. So we are trying to, essentially, we can create a kind of an ontology of the patterns, right? Starting from the more general one and going down depending on, the specialization of the structure that is useful for someone that is implementing the backend. So these are things that we can accumulate in the course of the extension of the library, in a sense, if you want. And so here what I'm saying is that, for example, a general is a general matrix. So here we are implementing these in terms of like static tuples as types. So then we say a square matrix is also a general matrix and a square matrix. So we are adding information in a sense within the tuple. And this creates kind of a partial order, and we can use these we can define a is-a relation on top of this partial order, and we can use it for type traiting kind of controls at the compiler level. And so here I just wanted to briefly, time still allows, seems, show essentially in the reference implementation how this can be captured, all this information can be used to, for example, build a matrix implementation, right, that takes structure into account, and is general enough that if you plug any of the patterns supported by the system, it will still compute correctly, okay? There's no high performance in here. It's just the way we could, take this information and create a reference implementation for the simplest of backends. So, sorry. Here, what I'm having is the three matrices, right? So the LP matrices with some structures. We have also the add and multiplication monoids coming from the semaring that we want to pick. And you have some static properties, like for example, the bands and whether something is symmetric or not can be captured as a const or a const expr and used in the implementation. And then here what we do is, as commented in green, we are basically doing some kind of polyhedral manual set intersection of things. So you can think of it as, we imagine that we are using a polyhedral tool, and we know that we have these 45 degrees bands, and so what would be the intersection or union depending on what we need here? So this is semantic dependent on the primitive, right? So for matrix multiplication is essentially kind of an intersection of bands. And we can plug these into the loop. So the loop will just perform the matrix, the addition and multiplication needed, right, without touching zero elements, logically speaking, right? And so the get storage index is, as you can see, the transparent access to the storage polynomial. We don't know what's the storage polynomial, it's plugged in. But we give the ij coordinate that comes from the iteration space carved down by the band's constraints, essentially, for example. And this will give us, if it's statically defined, the storage polynomial and all the row and column maps, this will provide, the compiler the ability to pick a single formulation. There won't be any function indirections in this. And we can get access to C, we can get access to A and B. And then we can apply the operator of the monoids to compute what we want to compute, right? So we have tried to, from an expressive point of view, we tried to introduce the structures that we needed for some important LAPACK functionality. So we have tried to implement eigensolvers, singular value decompositions, different kind of factorizations, Householder, QR, Cholesky, LU, and so on. And, basically what we stressed here is the use of the structures, the logical inference to make sure we are using the right structures in input and output to functions and things like this, right? So this was no performance behind the scene. But we also tried to project some performance. So here, what I'm showing is the Cholesky decomposition implemented using ALP-dense, and where we plug Kumpen BLAS, which is essentially the specific BLAS implementation for the Kumpen processor, for the sequential or the parallel block. So you can think of it as the classic LAPACK approach, right? So LAPACK builds on BLAS. So you express the algorithm and you exploit BLAS for your performance, in a sense, right? So we have not implemented the BLAS in ALP-dense. And as you can see, in the first plot here is the sequential one. So we are essentially following the performance curve of the traditional LAPACK plus Kumpen BLAS, okay? We are a little bit better because we realize we are actually using a better algorithm than LAPACK. I'm not going into the details, but you can still get actually a 2x just by using the appropriate algorithms. There is a bunch of algorithms, a family of algorithms that one could use for implementing Cholesky decomposition. And LAPACK, the open source at least, not the specialized ones, are using one that is not really the best choice. But essentially, if they would use it, I'm pretty sure they would also fall here. I'm pretty sure about that. And on the other, but here, we are using the traditional matrix storage layouts and so on. Here, instead, we are trying to implement the BLAS, in a sense. We are trying to do a shared memory implementation, parallel implementation of matrix-matrix multiplication, which would be implemented using GEM in BLAS, okay? And, but what we are using here, as you can see from the bottom thing here, is this multidimensional storage layout that I was discussing. So the get storage index function would try to plug it to retrieve values from this kind of storage layout. And as you can see, it's providing very good performance. And what happens is that the very same matrix multiplication algorithm was implemented as for the sequential in the same manner for shared memory. What was changing was just the formulation of the storage layout, essentially, that we plugged behind the scene. And we have some future extensions that we are interested in exploring. So everything that I've shown in the context of the reference backend can be thought as a blueprint for potential strategies at a compiler level. So every information that I manually captured and used to, to do this kind of optimizations can be clearly exploited by a compiler. So we are exploring the possibility to plug, to gather this information at the compiler level, and we are interested to do this perhaps in a multi-level IR settings like MLIR, where we could also apply some, high-performance strategy in the implementations. Capturing also entry patterns. Here I was focusing on non-zero patterns, but there are also important entry patterns that could be captured by maps. For example, symmetry, a different form of symmetries, or maybe even particular matrices like Vandermonde matrices or things like this, which could, in a way, minimize or optimize the space and the storage that you use, just because of the mathematical property of the relationship between entries in the matrix. On the other hand, we have ALP GraphBLAS, which is essentially sparse linear algebra. We have ALP dense. It would be very interesting if you would just have a single unified linear algebra API, where if needed, you can plug different concept of semirings, or if you want, you can express structures, and both in a sparse and dense case, you could maybe exploit that. So right now we're keeping this in a silo settings, but it would be very interesting to exploit these in the more general linear algebraic domain. And then multidimensional arrays would be also very interesting to investigate. So how to apply all this logic the moment we go to tensors. But we haven't really touched that yet. I want to finish with this picture and take any questions.
So these structures that you are extracting, are you extracting it manually? Like basically you look at the matrix yourself and then you convert it to some small, like a tuple of different pattern that exists in the matrix, right?
So at which point you mean?
So at the beginning, because I didn't see any specific program that goes over the matrix and extract the structures. I assume you know the structure of the matrix. And
yeah. Correct, yes.
And you
the
write
user
it as
would
a
express the structure as part of the type of the matrix, yes.
I see. And that basically just works for symmetric and, but when because you said something about the piecewise. So are you referring that you want to extend this to have, let's say you have a matrix with 1,000 different patterns, like let's say some part is like blocks, sometimes it's just symmetric, some parts like, so you're saying your tuple is going to have like 1,000 different types for each of those regions?
So this is something we don't do. So the only piecewise thing that we really tried to implement was the piecewise formulation of bands. So suppose you have
bands.
a matrix.
So that's you have two bands, and for each band
for
you
example,
have one. I see.
So essentially you would not go through the zeros in between the bands. You would just really focus on the bands. But of course, one could think of piecewise in a more general context, right? So maybe you have different areas of the matrix and different properties over the different areas, right? So that's what you're referring to. Yeah, absolutely. No, we haven't really touched that. But I'm pretty sure that, so in a sense, what we have tried at first here, since we also don't have automation, we wanted to first implement the reference backend manually just to practice with it. And we are using metaprogramming for all this, right? So we were striving for finding a minimal set of information that would allow us to express things like a LAPACK to some extent, right? So, and we found out that in scientific application that use a LAPACK, 45 degrees bands are good enough, so we don't need to have a polyhedral, set intersection implemented in metaprogramming, but rather we can simply, do interval analysis in a sense, and that would be good enough, right? But yeah, essentially the moment we jump into the compiler space, and maybe we will try things at an IR level where we could have maybe a richer set of tools as well, than not just the metaprogramming compiler. I think that could be very interesting to then explore different ways of expressing localized properties, for example.
Okay.
But right now, I would say we don't have that, and probably I would not do that either in metaprogramming.
And there's some relevant work close to this. I'm going to discuss it offline with you.
Cool.
Thank you.
Yes. So.
I have a small question then. Does this representation extend to also trapezoidal matrices? Or I can see that you're mostly focused on square matrices.
Yeah, absolutely. In fact, we use a trapezoidal type structure formulation for some of the algorithms, because LU, for example, in its most general form, you could express it as a trapezoidal upper or QR as well. So we have used that in here. But again, right now it's So essentially we showed that we could express it, but we haven't really done any particular high performance implementation based on that. But yes, we did capture that.
I guess I have one more small. So if you're going to, how do you imagine this being used at a higher level? For instance, by MATLAB programmers or whoever. So there you need some kind of dynamic measure of which representation to choose, because I guess now there are suddenly myriads of different representations
Absolutely,
that you can choose from.
So we are currently exploring something that I haven't mentioned here. We call these two paths, we call them transition and embrace path. This is also something we are trying to sell internally in the company in a way because product lines are typically very careful in integrating things. So the transition path means essentially you have your classical HPC approach of the performance stack, so LAPACK, BLAS, right? One thing is that we could, for example, take BLAS interfaces and provide just the appropriate API wrapper for those APIs, right? So you have your BLAS implementation. Behind the hood maybe is written in ALP-dense, let's say, and then we have compiler logic that allows to, because one of the goals is portability. So we would like to reduce the effort of rewriting BLAS, let's say. So the transition path would allow something like this, because you could write the BLAS once in ALP-dense and then maybe port it to a new architecture. The moment we will have the high-performance backend, this could also mean a compilation specialization for the new architecture. But would not require you to change your application, because if you're still using BLAS, you could still plug it in. The other is called embrace, in the sense that you embrace the API. So you say, okay, I'm happy to break the silos traditional approach. So we could take Cholesky decomposition and re-implement it. So this is obviously the one path that would give you the best, that could exploit at best the approach. But yeah, so interoperability is kind of an important thing that we are trying to explore as well. So how do we, establish within the current stack a connection, and how can we plug this logic into that?
Any more questions? Okay, let's thank Daniele again.
Thank you.